Hey everyone! If you are currently staring down a massive polynomial functions exam and feeling, well, maybe a little overwhelmed, just take a deep breath. You're in exactly the right place. In this explainer, we're going to dig into some real chapter tests and top-tier study resources to map out a step-by-step game plan for your success. We're going to break down complex algebra, decipher those tricky graph behaviors, and figure out how to turn those intimidating long-form questions into really easy points on test day. By the time we wrap up, you're going to be walking into that exam room feeling absolutely confident. Let's get into it. So here is our strategic roadmap for this review session. We'll start with general tactics for acing the exam, then tackle mastering graph transformations. From there, we'll look at spotting polynomial symmetry, move on to factoring and remainders, and finally, we'll put it all together.
Okay, let's dive right into our first focus area, acing the polynomial exam.
Now, you might be thinking, I just need to memorize the formulas, but knowing the math is honestly only half the battle. Knowing how your teacher is grading you, that's the real secret to a perfect score. The most absolutely crucial exam tip is hiding right here in plain sight in these test instructions. Notice how it specifically points out that you'll receive a communications grade out of 10 purely based on how well your math is presented. That means showing clear, step-by-step work is just as vital as finding that correct final answer. If we just rush through some complex polynomial division in our heads and scribble down the remainder, we're literally throwing away massive points. Treat your written solutions like you're explaining them to someone else. If you structure your logic and write clearly, you're going to secure those 10 free communication marks.
All right, let's move on to our next hurdle, mastering graph transformations.
Staring at a huge algebraic equation and trying to figure out how it moves on a graph can cause instant panic, but transforming a parent graph really doesn't have to be intimidating if you know the 4 golden rules. Think of these as your visual shortcuts, which is especially huge for multiple choice questions. First, if you add or subtract a number on the outside of the function, the graph shifts up or down. Pretty straightforward, right? Second, if you add or subtract inside the function, the graph shifts left or right. But here is the trick, and you really need to remember this. The results are counterintuitive. A plus sign actually moves it left, and a minus sign moves it right. Third, multiplying by a number affects the shape. Values greater than 1 kind of pinch the graph, while values less than 1 stretch it out. And finally, flipping the graph upside down, that happens simply by making the function negative.
And this brilliantly illustrates a core mathematical concept. We really need to stop seeing complicated algebraic expressions as a terrifying jumble of numbers and letters, and instead see them as single, movable objects. Once you view a polynomial function like a single object, those 4 transformation rules act like a steering wheel. They allow you to drive that object left, right, up, down, or flip it around the grid with total control.
Let's test drive that steering wheel with a real exam question. Here we've got a basic parent graph, y equals x cubed, and it's transformed into this much longer equation. So let's break it down using our rules. Inside the bracket, we have an x plus 3. Because it's inside, we know for sure it's a horizontal shift. And because it's counterintuitive, the plus 3 actually means we translate 3 units to the left. Then, at the very end, completely outside the function, we have a minus 2. That means we shift down 2 units. Finally, we're multiplying by 3/4, which affects our shape by horizontally stretching it. See? If we just read the equation left to right and apply those visual rules, we've totally solved a complex exam problem without having to graph a single point.
Up next, let's look at another game changer. Spotting polynomial symmetry.
This is another incredible visual shortcut that's going to save you incredibly valuable time on test day. There are basically 2 main types of symmetry you'll be tested on. First is line symmetry. This just means there's a vertical line, usually the y-axis, over which the polynomial remains completely unchanged when reflected. It's basically a perfect mirror image. Second is point symmetry, which you might also see called rotational symmetry. This means there's a specific point, often the origin, where if you were to literally pin the graph and spin it 180 degrees upside down, it would look exactly the same as when you started.
Now, what's really interesting about this is how perfectly these visuals demonstrate the connection between symmetry and function types. Looking at that perfect U shape, it's got line symmetry straight down the middle. If you fold it in half, the sides match perfectly. This visual instantly reveals that the function behaves as an even function. On the other hand, we have a graph curving up into the first quadrant and down into the third. If you rotate that 180 degrees around the origin, it's totally identical. This point symmetry tells you right away that you're dealing with an odd function.
But hey, remember those 10 communication marks we talked about earlier? The teacher isn't just going to take our word for it based on a drawing. You usually have to verify this symmetry algebraically, without graphing anything. For an even function with line symmetry, you have to prove that f of x equals f of negative x. So you simply plug negative x into the equation, and if you get the exact original function back, boom, it's even. For an odd function with point symmetry, you have to verify that f of negative x equals negative f of x, meaning when you plug in a negative x, the entire resulting function is the exact negative version of the original.
And that brings us to question 12 from this exam. You're given a sketch and asked to state whether it's even or odd ordered, and you absolutely must provide a reason. Because you now possess these visual tools, you can just look at the sketch, instantly identify whether it has mirror-like line symmetry or a rotational point symmetry, and immediately write down your answer and your reason. You're saving precious time and securing your points.
All right, moving right along to the big stuff. Section 4, Factoring and Remainders.
We are now officially entering the algebraic engine room of polynomial functions. This is where the heavy mathematical lifting really happens. So, the crucial point here is establishing a rock-solid step-by-step logic for your long-form calculations. Step 1. Always carefully identify your linear factor or divisor, like x minus 2 or x plus 1. Step 2. Decide your attack plan. You can either set up synthetic division to find the full quotient, or if you only need the remainder, just efficiently apply the remainder theorem. Step 3. Analyze the result. If your remainder is a flat 0, congratulations, you just found a perfect factor of the polynomial. If it's a specific value, well, that's your remainder.
And speaking of the remainder theorem, check out question 15 from the test. It simply says, state the remainder theorem, and it's worth 3 knowledge points. You guys, this is a massive wake-up call. Don't just practice crunching the numbers over and over, you actually need to memorize the core mathematical definitions and theorems. Be prepared to explain the math in plain English.
Because right after that, you'll be asked to put that theorem to work, like in question 10. They're asking for the remainder when a massive degree 4 polynomial is divided by x plus 6. Doing long polynomial division here would take ages and totally invites simple arithmetic errors. But because you know your step-by-step logic, you recognize you can just use the remainder theorem. You take the root of the divisor, which is negative 6, plug that negative 6 into every x in that massive equation, and whatever number pops out at the very end is your remainder. It takes a huge, scary problem and makes it systematic and completely stress-free.
Okay, we've reached the final stage. Let's see how all this builds in section 5, putting it all together.
Behold the grand finale of the exam, the blank grid. This is usually the highest valued question on the whole test. You'll be given a complex polynomial equation and asked to sketch it in detail. And this is exactly where we synthesize everything. You're going to use your factoring skills to find the x-intercepts or zeros. You're going to look at the leading coefficient and the degree to determine the end behaviors, where the arrows point off the graph. You'll check for line or point symmetry to help mirror the curves. Literally all those distinct tools we just reviewed are layered together right here to sketch highly accurate quartic or quintic functions.
Before we wrap up, I want to leave you with this final, somewhat provocative test question. It asks to determine the maximum and minimum number of turning points for the polynomial function g of x equals 4x to the 4th minus 5x to the 5th plus 2x squared minus 7. Do you notice the trick? The terms are totally out of order. The highest exponent, the actual degree of the polynomial, is 5, making it an odd degree quintic function. Knowing the rules of degrees and turning points, how many times can a degree 5 polynomial change direction at most? And how about at a minimum? Try applying what we've unpacked today to decode that for yourself. Honestly, once you can visualize these shifts and symmetries, you are going to be ready for absolutely whatever this exam throws at you. You've got this.